Welcome to 25th class meeting of EECE574, the graduate level probability and random process. Homework 13 will be assigned, as always assigned. Handouts are downloadable, so you can download. I didn't update it, so anyway. We are covering chapter 6 of Peebles, but a lot of parts are augmented from our graduate textbooks. So you may say that it's in between undergraduate and graduate level material. Especially we are studying the temporal characterization related random processes part. I hope we can also cover this frequency domain characterization of random processes part. No corrections or clarifications, but I will explain again about the Poisson processes and related definitions, such as counting or arrival processes, inter-arrival processes, something like that. Got it? So last time we studied the definition of jointly wise and stationary random processes, jointly stationary random processes, and independent random processes. These definitions are very straightforward. If you remember the most important theorem in random process, that is the Kolmogorov's extension theorem. So what was the joint wise and stationarity? In order to talk about this, you have to have two random processes. What is this? Okay. X of t and y of t. And if you remember correctly from the Kolmogorov's theorem, you have to find some random vector from x and y. So what you do is that you choose some vector of time instance t underscore and possibly different lengths time instant vector s. And then you may say that this strange notation means x of t1 through up to x of t m. And this s means x of s1, sorry, y of x s1 up to y of sn, something like that. Got it? So then you talk about independence, you talk about uncorrelatedness, you talk about orthogonality and those stuff. Probably I skipped the definition of orthogonal processes. So probably I have to talk about it today. Anyway, so if you just extend the Kolmogorov's approach to a single random process now to two random processes or multiple random processes, it is very important to construct a random vector from random process X, a random vector from random process Y, and then talk about possibly first what? Independence. So independent random processes. What does that mean? For any m and for any m tuple t, for any n and for any n tuple s, you form length m and n vectors from two processes, and if their joint distribution factors, then it's independent. So it's kind of obvious, right? So you may say that, okay, joint CDF of two random vectors for all choice of m and n and for all choice of sampling instance. Then they are independent random processes. this also extends to any finite number of random processes. And also, you can extend it to countably infinite number of random processes. So given countably infinite number of random processes, how do you want to define it? Probably you choose one more integer for any L integer. So among those countably infinite random vectors, you choose first L random vectors, and then you take samples and then talk about joint independence of those random vectors, something like that. What about stationarity? When do you want to define two random processes are stationary to order 1? Stationary to order 1, it's very hard to define because if you are given two random processes and you take only one time instant, where it doesn't make much sense. So probably you want to talk about stationarity to order 2 first. And then what do? Again, there is difficulty. You may choose 2 time instance from X only, 2 time instance from Y only, 2 time instance, 1 from X, the other from Y. But the previous 2 just talks about stationarity of each random process to order 2. So the X is stationary to order 2, Y is stationary to order 2, and here comes something interesting. So you find the joint CDF of 2 random variables for any time instant TNS. And then stationarity means what? If you add the same time offset to T and S, this joint CDF must not change. So T plus capital delta, Y, S plus capital delta, X comma Y for all X comma Y and for all delta. And of course for all TNS. Got it? And you may extend this idea to joint stationarity to order N, and also up to strict sense joint stationarity. Not only for 2 random processes, 3 processes, countably infinite number of processes. Motivated by joint stationarity to order 2, we may just say that, well, it's too complicated to handle joint distribution. Why don't us to handle expectation instead? Then we have joint Y-sense stationarity. So motivated by this one, X is Y-sense stationary. What does that mean? Mean path is constant, not necessarily 0. And X random processes autocorrelation function is function only of tau. So you can abuse the notation like this. So mu x t equals mu x for all t. And the other one is mu y of t equals mu y for all t. The first one is the autocorrelation function of y is function only of time difference. And eventually, you have the 5th condition that is strongly motivated by this one. What is that? The cross correlation function is also function only of tau. Ready? So joint Y-sense stationarity requires individual Y-sense stationarity plus the autocorrelation functions special property. Got it? What about the definition of orthogonality of two random processes. So let's recall what was the meaning of orthogonality of two random variables or vectors. Orthogonal, what does that mean? By definition, orthogonality means what? Correlation function equals what? Zero matrix. Got it? So, of course, when x and y are two random variables, what is that? R sub xy equals expectation of x times y. That is 0, right? But when you have two random vectors, you need to compute the outer product and then take the expectation. So you have a random matrix. Of course, it's rank 1, but anyway, if you take the expectation, then you have a 0 matrix. In that case, the random vectors are called orthogonal. What about orthogonal random processes then? Again, you combine this idea from the random vectors with the Kolmogorov theorem. Got it? So here goes the definition. Two random processes, x of t and y of t, are orthogonal. Orthogonal if you need to have random vectors. So for every m, for every n, and for every m tuple, and for every n tuple, right? X of t vector and y of t vector. So you need transposition here. Then this expectation equals 0 matrix. Got it? So for every m integer, for every n integer, and for every m tuple t, and for every n tuple s, if you take a random vector x of m tuple t and random vector y of, s, y of s, then their correlation matrix is a 0 matrix. What is the consequence or kind of corollary when you have two orthogonal random processes? Of course, if you sample at the same time instance, then what? Then this is a scalar 0, right? So here, this is a special case where your m equals 1, n equals 1, and t and s are the same as t0, right? So, but be careful, your orthogonality not only requires two samples taken at the same time instance are orthogonal, but different time instance also must be orthogonal. But not just only these two things, but if you take a careful look at this matrix, actually its ij's entry means what? You have ti y of sj equals 0 for, so actually, what does this mean? This definition is equivalent to that one, okay, for all t1, t0, and t1, okay? So these are equivalent, but not this one, okay? This is a consequence, but any two sample, if you take any two sample, one from x, the other from y, if their correlation is 0, which means that orthogonal, then two random processes are orthogonal. Okay? Be careful, orthogonality utilizes expectation. So if your definition involves correlation matrix only, then if you take a look at the ijth entry, then actually you only need this one. Got it? Anyway, so we've covered what was missing from last class meeting. And next topic was Gaussian random processes. And I told you that never think that Gaussian random processes are all Ysen stationary. Okay, be careful because usually communication engineers handle too many Ysen stationary Gaussian random processes. They just prone to believe that Gaussian random processes are always Ysen stationary, but it is not. Got it? You can just simply add arbitrary non-constant function to a Ysen stationary Gaussian random process, then still you have a Gaussian random process. Anyway, let's recall our definition. What was that? Again, we rely on Kolmogorov's approach. So we take an integer n, and we find an n tuple t, and then what? We consider a random vector x of t underscore. If this random vector is a Gaussian random vector for any choice of n and for any choice of n tuple, then this process is Gaussian. Got it? Now, let's see some special cases. First one is, of course, Ysen stationary Gaussian. Ysen stationarity means mean is constant and auto-correlation function is a function of time difference. But from the definition of autocorrelation function and auto-covariance function, you can easily see that Ysen stationarity implies autocovariance function is also a function of time difference only. Got it? And our definition of Gaussian random process has a consequence of what? The joint characteristic function of that sample follows, of course, Gaussian characteristic function, right? So let's change this. So anyway, so from the definition, from this result, if you take a look at the characteristic function, it only involves the mean path of the random process and autocovariance function of the random process. Got it? So the first important thing is that a Gaussian random process is fully characterized by its mean path and the autocovariance function. But you can also say that equivalently mean path and the autocorrelation function. Got it? Because you can always find the autocovariance function from the autocorrelation function and the mean path. And Ysen stationarity means what? This mean path is constant. And what? And your autocovariance function is the function only of time difference tau. Got it? And also you can easily see from that result, the characteristic function, then you can say that Ysen stationarity for Gaussian random process if and only if strict sense stationarity of the Gaussian process. So let me draw a Venn diagram in order to clarify the relations. So suppose this is the set of all Gaussian random processes. Then, of course, here is covariance stationary Gaussian random processes. And covariance stationary random process is not Ysen stationary because its sample path can be a function of t. And here goes y sense stationary means strict sense stationary Gaussian random processes. So this shaded area means what? Non-strict sense stationary Gaussian random processes, or non-y sense stationary Gaussian random processes. So there are many. Among these, one of the most interesting process was so-called the set of Wiener random processes. And Wiener processes are what? Gaussian random processes, but it shares a lot with the Poisson processes. The first thing is that we usually set x of t equals 0 equals 0. So at time origin 0, we set the value is 0. And then if t1 is less than t2, then x t2 minus x t1. This is called the increment on the interval t1 and t2. Okay. And this is called the increment on the interval. And this is what? This is Gaussian random variable with mean 0 and variance some constant times, let me say alpha, times t2 minus t1. Okay. So the variance of the random variable x t2 minus x t1 increases if t2 minus t1 increases. And it makes sense because if t2 converges to t1, the variance converges to 0. What does that mean? Gaussian random variable with 0 variance, a constant, 0. So x of t1 becomes x of t2 in that case, right? And what else? If you have two intervals, non-overlapping, then we have independence. So this is the first condition. This is second condition. The third condition is independence, independent increments, when the intervals are not overlapping. Of course, if they overlap, they are dependent, right? Anyway, these are all about Gaussian random processes. Okay, first order stationarity does not mean Y-sense stationarity or something, because first order stationarity means here the distribution does not change as time evolves. But still you have second order distribution dependent on the not only the time difference, but also the time instance t1 and t2. It's possible. So what can we say? Okay. Yeah, what can I say? We may construct a very strange random process like this. For every rational number, you have zero mean Gaussian random variable x. And for any irrational number, t, irrational time instant, you have another Gaussian random variable, y, that is negative x. In that case, you have distribution, first order distribution, just zero mean Gaussian, right? But now, if you choose two sample points, but if you choose T1 and T2, whose difference is for example, 1. But if they are, be careful, be careful. Yeah, it's time difference only in the case. Rational. Okay. Anyway, you can construct strange random processes. Yeah, I cannot come up with a very good example immediately. Anyway, so let's go to this section 6.6 again. We are going to redefine the Poisson random process. So first, before we talk about Poisson random process, we want to talk about the counting process. And counting process means that it could be discrete time random process or continuous time process. It doesn't matter. What is important is that the value of random process is related to the number of something. So you count something from time 0. So your sample path starts from 0 value at time 0, whether that time means discrete time or continuous time. And then as time evolves, you count always increasingly. Okay, so your value could jump to 1, jump to 3, something like that. Of course, among counting processes, you may define one group where you only allow single increase, single unit value increase or 0 increase at a certain time instant, or you may allow multiple counts. But usually, when we define a continuous time counting process, we restrict our discussion to those who do not allow multiple arrivals. Because anyway, if there are, for example, 5 persons come to our store, if I take a very fast photo, then as in Olympic Games, then probably there is a first arriving customer and second arriving customer. So usually for continuous time counting process, we do not allow multiple arrivals at the same time instant. So the sample path always goes up by 1 or does not go up for continuous time counting process. But for discrete time counting process, it's a little bit subtle. Okay, because if you allow multiple arrivals, sometimes it becomes very hard to analyze. But anyway, there are 2 types. But in both of the cases, you have discrete random process because anyway, there is no 0.3 persons, right? You always increase by unit value. So you may always say that the counting processes, whether it is discrete time or continuous time, they are all discrete random processes. Given a counting process, you can derive or find 2 equivalent random processes. And these are all discrete time random processes where the original counting process is continuous time or discrete time. Because the first thing, the arrival process, which is the abbreviated version of an arrival time process, you have discrete time random process S sub t. For example, you have S for discrete time counting process. S1 means the time instant, value of time instant where your first arrival occurred. So for example, your realization of S1, S2, S3, could be something like 1, 3, 7, 11, blah, blah, blah. What does that mean? Given the discrete time counting process, what happens at time 0, your value is 0. And at time discrete time 1, you have single jump. And then to 3, and 4, 5, 6, 7, 8, 9, 10, 11, something like that. Got it? So from this discrete time random process, the arrival time process S, you can find this continuous sorry, you can find the discrete time counting process. What about continuous time counting process? In that case, your realization could be some real numbers like 0.25, 11 point something, irrational number, something, something, something. So what do you see? You see something like this. Given a discrete time counting process, your arrival time process is what? Not only, of course, discrete time random process, but also a discrete random process, right? Because time is discrete. But for continuous time counting process, your arrival time process is a discrete time process, but it's a continuous process. It can take any value, right? Now, we define the third one, inter-arrival time process. That is denoted in our lecture note, x1, x2, x3, dot, dot, dot. Since this time index is all natural numbers, it's obviously a discrete time random process. But how do you define it? x1 is defined as s1. x2 is defined by x2 minus s1. x3 is defined by s3 minus s2. So now you see why we call the arrival process as S sub n and the inter-arrival time process as X, because as you see, this is x1 plus x2 plus dot, 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 xn. Because as you already know from high school math, if you rewrite them and or sum up, then on the right hand side you have S sub n, and left hand side you have all the sum of inter-arrival times, right? Got it? And you may say that, okay, there are three equivalent random processes. So what? Actually, sometimes we define this counting process not immediately by utilizing our Kolmogorov's extension theorem to that. We rather talk about the property of, for example, inter-arrival time process. And then we say that we have full characterization. Got it? Anyway, now let's see from our definition some simple but at the first glance very complicated consequences. So these definitions, set of definitions are applicable not only to discrete time counting process, but also continuous time counting processes. Let's restrict, okay. Let's use t as our time index. Got it? So this could be n of t or n of bracket t in either case. And a continuous time or discrete time random process, n sub t, defined for t greater than or equal to 0, is called the counting process if these conditions are met. First, at time 0, the value is 0. No occurrence at time t equals 0. So t is 0, actually. Same thing, okay? But actually, not exactly the same, but your reference time is 0 and no arrival at 0. Second, this is what? The process evaluated at some time instant is what? The total number of occurrences or arrivals or something you want to define, okay? Something arrive, so something you want to count. And of course here t0 is greater than 0 because for t equals 0 we have defined. And here goes the properties. So n0 is 0. If t0 is positive, and be careful, n of t0 equals m, what does that mean? That is what? You have from 0 to time interval t0, including this t0, you have m arrivals. Now, you want to extend this one to include negative t, then here comes some confusing part. If t0 is negative, then what does that mean? N sub t0 equals negative m means, as you see here from an example, one arrival between t0 and 0, where 0 is not included and t0, 0 is included anyway, 0, there is no occurrence at 0. So anyway, you can include 0 and t0. If there is one arrival, then this value is what? Negative 1, okay? Am I correct? Just a second. Let me see. Yeah. So if arrival time t0 is negative value, t less than t, just a second. Yeah, n of t0. Something's not correct. Okay, just a second. One. Yeah, I have to say, yeah. So the left limit is negative m. Okay, I will correct this note. Anyway. Of course, it's always integer valued and it's always non-decreasing by definition. And as I told you, two types of counting processes. One that does not allow multiple arrivals. The other that allows simultaneous arrivals. By our definition, every sample pass of a continuous time counting process is right continuous, as similar to our CDF, right, of a random variable. Now let me ask you a question. What about the sample mean pass of a counting process? Does it inherit this property? So every sample pass of a counting process, especially continuous time, is a piecewise constant function which is right continuous. What about sample pass? As you can easily see, the mean pass is not necessarily a piecewise constant function, as we will see from the Poisson processes mean pass. And these are most confusing parts. So suppose you evaluate random process at S sub n. So it's like you mix the counting process and then an arrival time process. So counting process evaluated at S sub n, nth arrival. What does that mean? Of course, it's n, because by definition, Sn means nth arrival occurred. And by definition of our counting process, that is the value at that time. Got it? Now, if t is between Sn and Sn plus 1, so t could be Sn, then what is the value? N. But t cannot be Sn plus 1, which means that n cannot be n plus 1. So you have n sub t equals n. Right? And this is actually almost the same, but S sub Tn is less than or equal to t and less than Sn sub t plus 1. How can you show that? Actually, you can show left and right by using the previous properties. Anyway, again, our counting process, especially continuous time counting process, can be rewritten by using our arrival time process Sn. And here you have unit step function. And that you have nth jump at Sn. And two events in terms of arrival time process and counting process are identical. These two are identical events. So when you compute some probability of event in terms of counting process, you may find it easy to compute the probability of an event in terms of the arrival process or sometimes inter-arrival process. So you must be very versatile, okay? Again, these two events are identical events. And there are a class of counting processes whose inter-arrival processes have very special property. As we've seen in our review on the Wiener process, given a time interval, left endpoint included and right endpoint not included, what was interesting? Right point included, left not included. What was interesting? If you have, so this is T, T1, T2, T3, and you have two intervals, T2, T3, and T1, T2. Of course, you have some more like T1, T3, infinity. These four intervals are disjoint, right? And you can define so-called increment for each interval, especially for these two middle intervals. Let me use n because we talk about numbers. So nt2 minus nt1 and nt3 minus nt2. What does this mean? The number of occurrences between T1 and T2 excluding T1. So after T1 and before and including T2, how many occurrences? How many occurrences? Something like that. And this is called the increment associated with the interval T1, T2. This is the increment associated with this interval T2 and T3. And some counting processes have interesting inter-arrival times. Now, let's say that these are not only just samples, but also say SN, SL. Let me see. Be careful. I need to be careful. Yeah, I will not talk about. Yeah. Okay. First, let's talk about not inter-arrival time, arrival time process. Okay. Is it good? Just a second. Increment. Yeah. Just a second. Okay. Yeah, I better not say that. This is just increment, okay? The increments may have some interesting property like Wiener process. They may be independent, random variables. Increments may be independent random variables. And sometimes since they are random variables, their distribution may be dependent on the length of this interval. Some processes have that properties. Got it? Not just not yet the arrival time process, inter-arrival time process. Just given a counting process, the increments may be independent and stationary. Stationary means distribution depends only on the time difference. Got it? And Wiener process is not a counting process, but shares similar property to those counting processes in that the Wiener process has independent and stationary increments. Ready? Now, here comes the definition related to inter-arrival process or inter-arrival time process. As I told you, if we define xn as Sn minus Sn minus 1, Sn becomes the sum of x's. And if inter-arrival time process xn, which means time difference between consecutive arrivals, if this process, this is always non-negative random, each one is random variable, is renewal process if these inter-arrival times are i.i.d. random variables, which means that renew means that, okay, let me forget about the past. So from now on, now new arrival, then next arrival time is not dependent on my past. Right? That is called renewal process because the inter-arrival random variables are renewed, kind of. So let's go back to our definition of increment given a counting process. And given two arbitrary time instants, t1 less than t2, we have the corresponding increment. And as I told you, if non-overlapping time intervals increments are independent, we call the process, the counting process has what? Or the process has independent increment property. Wiener process, let me talk about again. The Wiener process is not a counting process, but it has independent increment property. And if the increment depends, as I told you, distribution depends only on the time difference, then we call the increments stationary. Okay. And as I told you, if these two properties combined, we have very interesting random processes. So here goes independent and stationary increments. So here the set of or the set of or, for example, continuous time random processes. And here we have independent increment property satisfying random processes. And here we have stationary increments properties. Then here you have what? The Wiener process. And again, interestingly, here you have the Poisson random process. So not only a counting process, the Poisson counting process, but also non-counting process can have independent stationary increments. And if a continuous time random process satisfies this property, and also if we just simply set random process evaluated at time 0 equals 0, then these are called, this shaded area is called the Levy processes, Levy random processes. Okay. Of course, we need something like with probability 1 and t is continuous, blah, blah, blah. Just a second, continuous. Just a second. Yeah. Sorry about that. Continuous. Just a second. Yeah. Probably I have to define this way. So we have yeah. Yeah. Continuous sample paths. then these are called Levy processes. Levy processes. Is it? Just a second. Something's not correct. Yeah. Yeah, something's not correct. Just a second. Yeah, I believe it's something's not correct. Okay. So just forget about this. Let me search for Levy process because I've kind of updated that one. Yeah, always try Wikipedia. Okay. Okay, continuity in probability, not sample path is continuous. Okay. So it could be a continuous time process or a discrete time process. See that? We have Wiener process and Poisson process. And so, yeah. So this part is wrong. I will modify that. So previous description is correct. Okay. So the shaded area is a Levy random processes. So you have Wiener process as well as the Poisson random process. And another example is sum of Bernoulli process. So what is the Bernoulli process? It could be 0 or 1. And if you have independent Bernoulli processes, and if you sum up, then again, you have a Levy process. So here, sum of independent Bernoulli random processes, possibly having different probability of occurrence. Ready? Now, let's go back to our Poisson random process. There are many different ways to define a Poisson random process. If you take a undergraduate level, but Department of Mathematics or Department of Statistics version of Poisson random process, you will see something formidable. They talk about the limit in defining a process. So some infinitesimally small interval, blah, blah, blah. And that is actually all related to what? The Poisson approximation to binomial random variable. Probably you remember that if we properly scale, so given a binomial random variable, we have two parameters, n and p. And in order to have Poisson approximation, what do? N times p is kept constant, and then we increase n. Similar process is involved in defining a Poisson random process as a continuous time counting process. And as you remember, if you have a binomial random variable, its limit is Poisson random variable. What does that mean? You have Poisson random process here that is related to not only the binomial random variables, but also that limit process, that limiting process. Anyway, so here goes some interesting definition in terms of the increment. So the definition goes like this. A Poisson random process is a continuous time counting process that does not allow multiple or simultaneous arrivals. And the definition goes like this. It has independent, stationary and independent increment, and that stationary increment is what? Sorry, just a second. The stationary increment is what? A Poisson random variable. Why? Because if you sample a counting process, the two numbers are always integers. And if T2 is greater than T1, the difference is always non-negative integer, right? So you have what? The increment is a non-negative random variable, whatever two time instance you choose, right? And it says that the increment is a Poisson random variable. And as you remember, Poisson random variable is parameterized by a single parameter, the so-called rate. And that rate is some constant times this time difference, T2 minus T1. What does that mean? N T2 minus N T1. That is the number of occurrences between 2 points, right? And this is what? This is a random variable n, so n factorial e to the minus lambda T2 minus T1 and lambda T2 minus T1 raised to the power of n, and n can be 0, 1, 2, any. Got it? And the definition is very strange, right? It just says increment is independent, and the increments are independent, and increments are stationary, Poisson random variable. And now, last time I claimed that n of t is a Poisson random variable. How can you show that? Because n of t equals n of t minus n of 0. So it's an increment. And you plug in, then you have what? Poisson random variable. Okay, so far so good. But have we fully characterized this Poisson random process by using these 3 lines? In order to answer that, you must use Kolmogorov's idea. So you have to ask yourself, can I find any first order distribution of this counting process? Second order joint CDF. Third order, fourth order, any nth order. Can I always find these any nth order CDF of the random process? And if your answer is yes, in terms only of these 3 lines, then these 3 lines fully characterizes the random process. So let's do that. First, this is the first order PMF, because we are now handling what? A discrete random variable, right? At each point. So we now have jointly distributed discrete random variables. So PMF is better. So first of PMF, what does that mean? You need to find the probability event that n over T1 equals some non-zero integer. You want to find this probability. And it's not that difficult because n over T1 equals n over T1 minus n over 0. So by definition of this increment, stationary increment, we have Poisson distribution like this. Got it? Do you see? Here, n is replaced by k1, that is the time, the value at T1, right? And this could be any non-zero integer. Now, second order. How can you find the second order PMF? The second order PMF is what? N of T1 equals K1 and N of T2 equals K2. And here we assume T1 is less than T2, less than or equal to. Yeah, less than makes sense, right? And of course, then K1 is less than or equal to K2. Okay, be careful. Even though T1 is strictly less than T2, these two values could be the same, right? Because it is possible no arrival between this T1 and T2. Now, in order to find this joint probability mass function, what do you want to use? You want to use independent stationary increment property. And you may say that, okay, in order to talk about increment, I have two time instance and I have two, what can I do? No. If you remember this first derivation of first order PMF, actually you have one more time instant that is 0. So it's like if this is time axis, you have 0 and T1 and T2. And you have two non-overlapping intervals. So you have n of T2 minus n of T1 and n of T1 minus 0, which is n of T1. Now, instead of talking about the joint distribution of these two, what about talking about joint distribution of these two and transform this joint distribution to this distribution? It's not that difficult, right? And you can use this transformation, or you can just immediately use the conditional distribution, the chain rule. So let's put this part under our conditioning bar. So n of T1 equals K1, because we already have computed in the first order PMF computation. So as you see here, the next part is what? Conditional probability of n of T2 equals K2, given n of T1 equals K1. And what does this mean? Given this condition, this event is same as n of T2 minus n of T1 equals K2 minus K1. And that event is independent of this event. So you have, again, Poisson distribution, now with parameter lambda times T2 minus T1. And number of occurrences is K2 minus K1. So by multiplying your derived first order PMF and this conditional PMF, what do you have? You have second order joint PMF. Now, let me ask you a question. What about third order? What about third order? You want to use just the derived second order distribution. So what you do is that for the third order, you have now 0, T1, T2, and T3. And what do you want to do? You consider conditional probability of event that n of T3 equals K3 given n of T1 equals K1 and n of T2 equals K2. Why? Because you can utilize what you have derived in the previous step. In that way, any nth order joint probability mass function can be found. Got it? So you are done. So these three lines fully characterizes this counting process. Because you have increment is defined as a non-negative random variable. It's always increasing. And this is what? A discrete random variable having non-zero integers is a counting process. Got it? Now, there's another definition now in terms of inter-arrival process. So given n of t, you have inter-arrival process xn, which is a discrete time continuous random process. Now, Now, we have something like this. This is t, and x1, x2, x3, blah, blah, blah. And this x means arrival time. First arrival time, second arrival time, third arrival time. Got it? So here your n of t is what? 0, and sudden jump to 1, sudden jump to 2, jump to 3, sorry, 3, something like that. Now, you can show that given a Poisson random process with arrival rate lambda. By the way, lambda is called the arrival rate. Why? Why this is so called? Let's think about n of t, which has distribution n factorial in the denominator and e to the minus lambda t raised to the power of n. What if you increase lambda? You increase lambda. Then what happens is that your random variable has higher n. Sorry, is it increasing arrival rate? Yeah, I believe so. If you increase lambda, then you have higher probability values in the, am I correct? Just a second. Something's not correct. Yeah, I believe I'm correct. So if you have a bigger lambda, then your Poisson random variable has distribution more clamped around this origin. Got it? So you have a faster increase. Got it? So, and also this lambda has unit what? Per second. So it is legitimate to be called a rate. Rate has always what? The unit of something per second. And lambda has something per second, arrival per second, and t has second, so you have a unitless exponent. And this is actually very important in physics and or mathematical modeling of real-world phenomena. Whenever you have trigonometric functions or exponential logarithmic functions, your argument must be unitless. For example, as you remember from information theory, what is the capacity of additive white Gaussian noise channel? C equals W. That's okay because it has same unit as C, BPS, W times log 2 base 1 plus P over N naught W. And your denominator N naught W has same unit as the numerator P, which is watts. Got it? Something like that. Anyway, so what we want to show is that inter-arrival time process is what? An i.i.d. exponential random variable. Okay? i.i.d. exponential random process. So each discrete time, each entry of the discrete time random process, x. So you have random variables, countable integer random variables, they are i.i.d. exponential. So arrival time is exponentially distributed. What does that mean? Exponential distribution has very fast decaying PDF. What does that mean? You may not, you have very light tail. Of course, it's not square, but anyway, you have light tail. So your highly likely inter-arrival time is somehow very short, of course, depending on the value of lambda. Okay? And as you see here, again, what is x? X has, again, second, right? And lambda has number per second, and they can be multiplied to form the exponent. And what do you have for the exponential PDF? If you have bigger lambda, then you have what? So this is PDF, and this is lambda, and so-called time constant is shorter if you have bigger lambda. So your arrival rate increases. You have shorter and shorter arrival, inter-arrival times. And it makes sense. And as I told you, you must be able to derive this result from those three lines and vice versa. Okay. And here was some interesting property. You know, or you can find the first order, second order, any order moment of a Poisson random variable. And this is not immediately related, but if you compute the expected value of the increment, okay, this is increment, then from the linearity of expectation, you have these two, and each one is Poisson random variable, and its mean is what? The parameter. So this is lambda T2, and this is lambda T1, and if you subtract, then you have this one. So lambda makes sense. In between T1 and T2, how many arrivals? This is what is the expected number of arrivals between two time instants, right? So it perfectly makes sense. We call lambda as the arrival rate. The arrival rate of the Poisson counting process. And as I told you, there are other definitions for the Poisson random process. And our lecture note class handout has some redundancies here. It shows the first order distribution and second order joint distribution, but here this is more systematic. After we find the first order PMF, then immediately we find the expected value, first order moment, and even second order moment. And here, take a look at the second order moment. In the second order moment, lambda t is a unitless quantity, and 1 plus lambda t, they are also unitless quantity. And what does this mean? If you subtract this, subtract the square of this one from that one. So the variance of n of t equals what? Lambda t plus lambda square t square minus lambda t square, which is lambda t. So interestingly, the variance and the mean are the same, right? As you've seen in the computation of the second order moments of the Poisson random variable.
Dr. Joe, it is time to wrap up. Dr. Joe.
Okay. Here goes the autocorrelation function, which is very interesting. So here, we want to compute the autocorrelation function of the Poisson random process, which is defined this way. And how can we compute this one? We have two jointly distributed random variables. So we need to double sum the product, the value times probability. But you have two variables, say K1 and K2. And you have joint distribution, but you can also do what? You can convert this to iterated expectation, as you've seen already, right? That is the idea. So you use the conditional distribution. Conditional expectation is averaged. This is total expectation theory. And by conditioning on smaller value K1, you have independence between this one and the difference. But there is no difference. So what you do is that you subtract NT1 and add NT1 here. So you have some procedure, then eventually autocorrelation function is what? Is not a function of time difference. So what can you say? It's not Ysen stationary. Of course, its mean is not the constant, lambda t. The sample path is a what? Continuous function. Constantly increasing function. So let me draw. So mean path of the Poisson random process is what? Is this one, lambda t. And this is drastically different from what? The sample paths. Sample paths are what? Piecewise constant, right? Continuous function. But its mean path is a continuous function, continuous, and you may say differentiable if you want to differentiate. Ready? And autocorrelation function as a function of T1 and T2. It has very complicated form, but of course here, this is unitless. And here, this is lambda times t. So this is also unitless quantity. But minimum, so you may say that these lines, this area has minimum something less than, probably I'd say that this is, if this is T0, this line, not the shaded area, this line means minimum is it minimum? Sorry, maximum, minimum. Okay. Sorry. Yeah. So on these lines, the minimum is T1, something like that. So our Ysen stationary requires that the autocorrelation function must be invariant on these slope 1 lines, but this is violated. So not only the first condition, second condition says that it can never be covariance stationary. So it's not a stationary random process. Okay, what else? The covariance function is this given by this one. And it seems we are done with the Poisson random process. Next time, we will talk about complex valued random processes, and then time average and ergodicity. Okay, that's all for the day.